Speaker of the day is Benjamin Mckay. He will speak on homogeneous holomorphic foliation on Kobayashi hyperbolic manifold.
Thank you. So I want to talk about homogeneous holomorphic foliations. And so let's think about, from now on, foliation means holomorphic non-singular foliation. And that's unusual. Most authors wouldn't be, is that all right? So most authors wouldn't be thinking about both homogeneous, both holomorphic and non-singular simultaneously. Okay? So from now on, that's what I mean by foliation. So let's think about some examples, simple examples of foliations. So some examples. Projective space has none. There are no holomorphic non-singular foliations, right? They have to have singularities. So that's already an interesting phenomenon. We could look also at the torus, the complex torus, so Cn mod lattice. And then we know that the generic holomorphic foliation has dense leaves. So the leaf space is non-Hausdorff, right? So it's rather bad in some sense. And it's not a compact phenomenon. It's the same, if you look at, say, C star to the n, also has generically dense leaves. When I say generically dense leaves, I mean the generic holomorphic non-singular foliation has dense leaves. So typically, these are rather bad foliations, right? These are rather bad foliations. Okay, so we might wonder about other examples, and my co-authors were particularly interested in these hyperbolic manifolds. So I'll explain in a minute what is Kobayashi hyperbolic. But as an example of such a thing, we found an example. So let's let Bn be the unit ball in Cn. And it turns out that it has foliations. And again, our foliations are holomorphic non-singular. It has foliations with at least one non-closed leaf. Non-closed leaf. Okay, so we don't really understand very well what happens with the ball. What are the possible foliations? It's surprising that it's a very simple object, and we don't really know much about its foliations. So the example I really want to think more about, that's more typical of what we're interested in, is the following. You take, again, the ball. So it's a unit ball or any ball, in open ball in Cn, but it's an open ball, right? And then you pick a point, P naught, which is not in the ball, but it's on the boundary. Okay, so on the boundary of the ball. And then what I'm going to do is look at all the complex lines that go through it. F, my foliation, F equals the complex lines through P naught, where they intersect, where each intersects the ball. I didn't write that very well, but so the intersection of each complex line with the ball, right? All the complex lines through P naught. And it's not hard to figure out what's the leaf space. So what's the leaf space? So we know that Pn minus 1 is the set of all complex lines through P naught. Sorry, what's that? They could be any dimension, actually, in this talk, as long as the only dimensions they can't be are 0 or codimension 0. Right? They can't be dimension or codimension 0. Otherwise, it doesn't really matter what the leaf space. But in this example, they have to be one-dimensional, because otherwise it really won't work. So you take all complex lines through the point, you get projective space. And then what about, if you look at Pn minus 2 is complex line, the set of complex lines through P naught, through P naught tangent to the boundary of the ball. And so if you take those away from each other, you get that Cn minus 1 is Pn minus 1 minus Pn minus 2 is the leaf space. Okay, so what we've got is a nice, pretty picture which we can draw, and which gives us a foliation by curves of the ball, and the leaf space, rather surprisingly, in some sense, large, because somehow the ball is very, well, we'll say what hyperbolic is. It's very hyperbolic, and this is very non-hyperbolic, which is a bit surprising. And also, another thing that's interesting is that there are a lot of automorphisms of the ball that fix P naught. Okay, the automorphism group of the ball is very large. Even if you fix a point on the boundary, it's still quite a large group. It acts transitively on the ball. So it's actually, this is a very homogeneous example. Okay, so that's the sort of example I want to have in mind. So let me just briefly say what hyperbolicity is. Okay, so I'll just briefly say what do I mean by complex manifolds being hyperbolic. Okay, so recall that the disk, well, this is the set of complex numbers with norm less than 1, and it has a unique constant curvature Riemannian metric. Which is usually known as something like the Lobachevsky metric or the Poincaré metric, okay, which we just call the hyperbolic metric. Which is it has to be unique invariant under biholomorphism. Okay, so that's the standard metric on the disk, right? The one with constant curvature, I should say constant curvature minus 1 metric. It's the unique one. Well, I don't even have to give it a constant as long as I scale it. So it's the unique metric on this guy that's invariant under the biholomorphisms. And so if M is a complex manifold, and P and Q are points of M, we let Km, oh, maybe I should give this a name also, has a unique constant curvature Riemannian metric, which is called K of the disk. Okay, so Km of points P and Q is the infimum of the set of all K disk, P naught, Q naught, such that, what do I want to say, such that P naught, Q naught are points of the disk, and there exists some holomorphic map with f of P naught is P and f of Q naught is Q. Okay, and so it's the infimum of that, well, union infinity, which is a possibility, right? Because there may be no such maps. But anyway, let's not worry about that. Let's let this be the Kobayashi pseudo metric, and the definition is that M is called hyperbolic, or Kobayashi hyperbolic, if Km is a metric, which is really the problem that we need to make sure that for all P and Q, P not equal to Q, let's say, we need Km of P and Q to be positive. That's the real issue, right? To make sure that you can't make holomorphic disks mapping that'll match up P and Q and that'll somehow be sort of very large disks in some sense. Okay, so this is the notion of hyperbolicity. Intuitively, it means it does not contain large disks. Okay, so that's what we mean by hyperbolic, and what if it doesn't exist? I won't worry about cases where it doesn't exist, since we won't need any. But right, what if there are no such holomorphic maps? Then let's just make it be infinity or something. Is that what I want? Yeah, I think. If there are no such holomorphic maps, yeah. I think, well, for a connected complex manifold, there are always such maps, so that's not the real issue. The real issue is the zeroness, right? So, for example, I won't prove it, but the ball is hyperbolic. That's not hard to see, right? It projects to various disks, so it's basically the Schwartz lemma. And Cn is not hyperbolic. Why? Because it has dilations, and so it doesn't preserve any metric. Dilations won't preserve a metric, inducing the standard topology. So yeah, it turns out that F always exists, which is not obvious. Yeah, there's a lot going on here that I'm not really exposing very clearly. Yeah, it turns out that you can make holomorphic disks go everywhere you want them to go. And yeah, so it's a bit of analysis to prove that. Okay, so what we have now is a, maybe I should say, okay, from now on, M is going to be a hyperbolic complex manifold, and then F is a holomorphic non-singular. I said I wouldn't even say these words, but now I'll say them. Holomorphic non-singular foliation on M. What do I want? I want G to be the biholomorphisms of M that leave F invariant, not fixing every leaf, but taking each leaf to another leaf, possibly different leaf. And then what else do I want? I want to let N be the leaf space. And then pi takes M to N is is the leaf map. Okay, so the leaf space is the set of leaves of the foliation, right? Induced with the quotient topology from this map, which associates to each point the leaf of the foliation through that point. Right? Okay, so that's from now on always going to be in the background. We'll use all this notation and terminology. Okay, so what do we want to do? We want to state a theorem. Under these hypotheses that N is a complex manifold, and pi takes M to N. Under these, again, this is the hypothesis, the setup here, is a holomorphic submersion. Okay, so that's the circumstance. Now it may see, oh, sorry, I need to have one more hypothesis. I need to assume, we'll assume, and this is a very strong hypothesis, which I should have put, because it isn't true at all in this setting. Assume that G acts on M transitively. Otherwise, it's nowhere near true. Okay, so what we're setting up is a hyperbolic manifold with a foliation. We take the automorphisms of that structure, we take the leaf space, and we assume, the only assumption here really is this one, that we have a transitive action of biholomorphisms, fixing the foliation, which is a rare phenomenon. It occurs here, but it's certainly a very rare phenomenon. And yet, even in this circumstance, we spent several years trying to prove this result. It was surprisingly hard. So what's really surprising in this example is that somehow, even though the manifold is hyperbolic, so this is in this example M, the leaf space, which was our N, turned out not to be hyperbolic, which we were surprised by. We were trying to prove they were actually hyperbolic as well. And that was really quite surprising. And it leads to this actually really weird result. In fact, we have a proposition that if pi takes M to N is a holomorphic fiber bundle map, then something strange happens. Then, in fact, M is actually N cross the leaf, the trivial foliation. The obvious foliation. The foliation is just point cross leaf, or whatever it is. Yeah, point cross leaf. It's the trivial foliation, and this is G equivariantly identified. So it's really, really trivial, okay? So if it's actually a holomorphic fiber bundle map, then everything's extremely trivial. So typically what's happening is somehow, if you try to construct such foliations, they come from submersions, but they don't come from fiber bundle mappings. So they come from maps that are nice, but not very nice, which is a little surprising. Okay, so the first trick I want to talk about is the notion that we got from a paper of Bachner, a very old paper from the 1940s, how to construct a decent set of coordinates. So we're going to think about what I've called Bachner coordinates. Bachner coordinates. Okay, so what we want to do is to construct nice coordinates, and so here's the lemma. Around each point M in M, there are holomorphic Frobenius coordinates. For this, we're going to use we're actually going to use hyperbolicity to get the whole thing. So that much is always true for any foliation. So they're holomorphic Frobenius coordinates for the foliation. But they're better than that. So in which the foliation is a product so it's trivial. It's a ball of some dimension crossed with a ball of some complementary dimension, right? So the leaves are ball crossed with a point. And so at least this is a very local picture, right? There are holomorphic coordinates in which you can actually match up the foliation by this product foliation, and the stabilizer, let's call it GM. So at some point, let's say I don't M naught. So GM naught is a subgroup of, in these coordinates, is a subgroup of the unitary group of the ball crossed with the unitary group of the other ball. Okay, these are the unitary linear transformations. It acts by simultaneously linearizing the entire stabilizer. Right, all the stabilizer of this point is in fact simultaneously linear. It turns out the proof is essentially just Bachner's proof, and you can really pretty much walk through his paper to prove this. It's interesting, though, that Bachner was thinking about Riemannian metrics and linearizing their isometries. But it turns out that the proof more or less works here, but we have to really use the condition of hyperbolicity. It's used in a somewhat subtle way, which I won't deal with in great detail, but the basic idea of the proof is that you take any holomorphic Frobenius coordinates, so Z1 to Zn, and then get the stabilizer to act. We have to worry about, can we do that? Is that possible? We have to note that G M naught preserves the Kobayashi metric, so preserves the balls, the Kobayashi metric balls, and we need to know some result, which I don't even have in my notes here, that it's known that it's known that the fact that G acts transitively implies that Km induces the standard topology. And that's not obvious, right? That's actually to do with somehow with, it's not always the case, right, that you'd get the standard topology. Is it? I'm trying to remember that. I'm trying to remember if I need the homogeneity to get that result or not. But so I think I need homogeneity for that. So we can somehow get it doesn't No, it doesn't imply the Kobayashi metric is Riemannian, no. So we can get a Kobayashi ball inside the coordinates, the coordinate domain. Okay, so we can find a Kobayashi ball because they're small. They can get them to be as small as I like. I can fit one inside the coordinate domain. It'll be invariant, GM invariant, because we're looking at the stabilizer of a point, so the balls around that point will be invariant. And there's balls that are so small they fit inside the coordinates. So we can fit them inside. And so, so now GM naught, this stabilizer, acts on that ball, on that Kobayashi ball. So we can make sure that there's a domain which is with an invariant action. And then we follow a recipe. We just do an averaging. I'll just write down that the new coordinates are given by averaging out over the stabilizer. You linearize the action in those coordinates. It's a bit tricky. You have to linearize the action in those coordinates, invert, and then you take the nonlinear action in those coordinates. Okay, so I mean, I don't want to go into detail into what that says, but more or less the idea is it's an averaging argument. You're going to average the old coordinates, but you have to try and do a G action and then undo it with the linearized version. So you do the nonlinear action and then you do the linearized approximation to that action. You average over all the possibilities, and then it's not hard to show that you do get the required results. So I'm not going to do the rest of it in detail, but it's exactly proof. If you follow the proof in Bachner, you get the rest of the proof of that result. So we have these Bachner coordinates, and my picture in my head of what they look like is that they're a product of balls. So they look something like this, like stacked up pancakes. You have these balls, okay? Okay, so you have these balls. So this is BK crossed with a point, and these we'll call plaques. Plaques. Those are intersections of leaves. So a plaque is the intersection of a leaf with a Bachner coordinate domain. Okay, so they're these little balls, and they're stacked up like this. Okay, and that's the picture. They're plaques. It's hard to draw them over and over again looking like pancakes, so it's easier to draw them flat as if you were looking at them from the side. And so I'll draw them like that. Those are the plaques. And then the actual leaves are more complicated. The leaves may go out and come back and make many plaques. So the same leaf could appear in many plaques, right? So our local picture is this plaque picture, and the global picture is that the plaques may or may not connect up with each other globally. So, right. So what I want to think about is how the leaves fit together outside of the coordinate domains, right? How do they match up? All right, so one important point about this Bachner coordinates is that, again, by homogeneity, the largest ball in the Km sense, Km ball, in each and every possible Bachner chart or Bachner chart domain around each point is the same size as any other, right? So because it's homogeneous, it looks the same everywhere. So if whatever size of ball you can fit in one Bachner chart, you can fit the same ball in the other chart and in the other chart. In fact, you can just grab the chart and just slide it over and make a new chart. So you can pick up your charts and slide them around and make new charts anywhere you want, and they all look the same, so to speak. They have the same size of balls inside them, in Kobayashi sense. Okay, so what I want to do now is to think about the following idea. We're interested, again, in these plaques, and we're interested in how they connect up and become leaves outside of the picture. Yep. No, M can never be compact. No, no. No, it turns out not. Yeah. Right. So what we're interested then is these things wiggling out, coming out, and then coming back again, and how they come back again. And we're interested in the first problem is are the leaves closed? And that's exactly the problem of whether or not can one leaf approach another. Okay, so that's what we spent a lot of time worrying about. Is it possible for one leaf, by wiggling back and forth many, many, many times, to get close to another, to a different leaf? And that's the problem of the closure of leaves. But it turns out the way that we found to think about this, which was helpful, was to imagine a leaf not approaching a different leaf. It turns out it was useful to imagine first a leaf approaching itself. Okay? So this question is a difficult one. It's easier to think about a simpler question, which is about a leaf approaching itself. So a point in our manifold is mad if there exists some Bochner coordinates and points Pn all in the leaf of P, but different plaques. And we might as well assume different plaques and Pn approaching P. Okay, so mad points turn out to be the right things to think about. It's hard to get anywhere with closed leaves, but it's not hard to get if you make the additional assumption that you're dealing with mad points, then it's actually much easier. So again, the picture is we have all these plaques, and the plaques are getting in close toward this plaque. Say they're getting in toward this one. Okay, and we've got points P1, P2, P3, ... and they're approaching some point P, but they're all on the same leaf. When you go outside the picture, they all end up on the same leaf, and somehow this leaf ends up being connected to that one. Okay, so there's all these plaques coming down onto this plaque, but they're all in the same leaf. Okay, so what we want to say is that lemma the lemma says either all leaves are closed, or all points are mad. Okay. So the crucial thing was to stop thinking about closed leaves and start thinking about mad points. This was the big breakthrough, one of the big breakthroughs. It took us 4 years to get this result. It was very painful. We had many false proofs. So, okay, so what do we want to think? We want to think about these mad points. So if not, so here's the proof. If not, so it's not the case that all the leaves are closed, and it's not the case that all the points are mad. Then let's see. What's that? Everything is transitive. So if one of them is closed, they're all closed. If one of them is mad, they're all mad. Right? Yeah. So it's good enough to prove it for a single one. Then some. Okay. So if not, then some P is what do I want to say? Okay. Then what I want to say is that some P is not mad. In the picture of these guys, you can't get in toward P on the same leaf. So you can't approach P on plaques of the leaf of P. Okay, so you can't get in toward it, and therefore that plaque is actually isolated among its leaf. Okay, so it's isolated plaque. It's an isolated plaque. It's just that plaque is the only one among its leaf, and so so we can change the Bochner coordinates. Bochner coordinates to get that plaque through P to be the only plaque of its leaf. Because there are only, say, finitely many other ones that are nearby. And so we can just restrict near P, make a smaller Bochner coordinate chart, and make P be the only, that's the plaque through P, be the only plaque of its leaf. So it isolates that one plaque. In particular, it shows that the leaves are locally closed. Okay, so we're still not done with the lemma. What we've got so far is we've got a point that's not mad. So near that point, if you get close enough, then it's got this, just the one plaque on its leaf. It's the only plaque on its leaf, and the leaves are locally closed. Okay, so so now what we want to do is take a non-closed leaf, and say. So Q1, Q2, we're no longer dealing with the P's, but with some other guys. It's these guys, and let's suppose they approach P. By homogeneity, I can make them approach anywhere I want, but they're all in the same leaf, which may not be the leaf of P. Okay, so we have another leaf now. We now have two leaves to worry about. We've got the leaf of P, which is locally closed. We now therefore know all the leaves are locally closed. We've got some other leaf with all these points on it, and they're coming in toward P. Okay, so we've got one leaf with all these points on it, Q's, and they're going toward P somehow. So now what I need to figure out is why this can't happen. Okay, if Qn gets close enough to P, so n large enough, then P sits inside the Bochner chart around Qn. So we forget about the chart around P and think about the one around Qn, which moves with n. We get different charts. But all the charts are the same size. As I said before, when we have these charts, you can translate them around using group action. It's a transitive group action on a manifold M. So you can move a chart around anywhere you want, and they're all the same size. They all fit the same Kobayashi balls inside them. And so once Qn gets close enough to P, P's inside that ball, and P's therefore inside that chart. So eventually, you get a picture where you get the chart not around P, but around Qn. You have the Qn sitting at the center of the chart, and somewhere in there is P. Okay? And then we've said then, by the previous result, the previous part of this lemma, we've already said that we can arrange the charts. We can arrange that there's only one, that our plaques are isolated. There's only one plaque in a chart, okay, in a Bochner chart, for a given leaf. So this leaf, we take the chart around Qn, its leaf only intersects here. It doesn't go back in again, okay? So Qn is on the single plaque of its leaf. That's on the single plaque of its leaf. But that means there's no other plaques in there to go to P. So no other Qn plus 1, Qn plus 2 points, ... going to P. What do I want to say? Qn plus 2, ... going to P. Okay? It's not possible to get to P because you're stuck on this plaque here, and there's no other plaques in there. So that means, therefore, that there's no way to get to P. Okay? So that's a contradiction, and that proves the lemma. That proves that everybody's, it proves that everybody's closed, or all leaves are closed, or all the points are mad. Okay? So that's the tricky bit. Concentrating on madness helped us to understand more clearly what was going on. But I haven't proven the main result. Still have to prove the main theorem. What do we know? We know at this point, so going back to our hypotheses, which I've probably wiped out somewhere, we have that M is a hyperbolic complex manifold, F is a holomorphic non-singular foliation, invariant under transitive group G. And what we've discovered is that the behavior is either very good or very bad. Either all the leaves are closed or all the points are mad. Okay, so they're really very close to their own leaf. Okay, so now what we want to do is show the next lemma is that the leaves are closed. Okay, all the leaves are closed. And the proof is suppose not. So proof suppose not. So so we're going to have some mad point. And then we forget about having to worry about leaves closed. We've got some mad point P. So we've got P1, and let's draw our picture again. So we've got a little pancakes, and we've got a stack of them. We've got a P1 on this guy, and so on and so forth, right? P2 here, and they go in toward P. Okay, they're all on different plaques. Okay, so so the P ends go to P, all on the same leaf, but different plaques. Okay, so we've assumed that such a point, we've proven such a point exists, right? We've proven that there is a mad point unless the leaves are closed. So we've got to figure out what happens near the mad point. Is that all right? Yeah. Oh, what if you did the chart around P instead of around Q? Then you'd only get the leaf of P being isolated, but maybe the Qs are not isolated near P. They'll be, eventually the Q ends will lie in plaques that lie inside. But if they're approaching P, they have to lie inside the domain around P eventually. So the leaf of P is locally closed, but then the leaves of Q could be, the leaves of the Qs could be coming down toward the leaf of the P, because they're all different plaques, right? So they can be locally closed and still approach somebody else. Yeah, it's tricky. So we've got, okay, so we've now got a mad situation here, and then what do we get? So here's the weird fact. Look at the picture. This P lies on entirely on this little disc, or well, it's really a ball, but it lies there, and this one lies on another one. So if you look from the point of view of the leaf is going off this way and coming back, and going off this way and coming back, and so on, and going off this way and coming back. From inside the leaf, this is discrete. So inside the leaf, what do we call it? FP. Pn does not approach P. It's actually discrete because each one has a ball around it. And you might say, well, what if those balls get small? But again, it's the sort of Kobayashi thing. They're all uniformly the same size. Okay? It's not too hard to show that they're all uniformly, by our Bachner coordinates story, they're all the same size of Kobayashi metric. Okay? So they don't get small. Inside the leaf, it's a long way to go from P1 through P2 to P3 and so on to go and end up at P. It's a long trip. It takes infinitely far to go that way. But this way, it's not so far. Okay? So inside the leaf, it's not approaching, but inside M, Pn is approaching. Okay, so what we can do now is, by homogeneity, what I'm going to do is I'm going to pick some elements of G. So it's a transitive group. So I can pick some elements so that Gn P is Pn. Okay, so I'm going to pick elements that move this guy up to here, and then up to here, and up to here, and up to here, and so on. Okay, so now what have we got? We've got these guys go to P, and now by a theorem of Kobayashi, which I probably should have mentioned earlier. By a theorem of Kobayashi, the fact that the Gn, Pn converge, and the Gn are in fact biholomorphisms of Kobayashi hyperbolic manifold, implies that the Gn, after maybe taking a subsequence, converge to G, okay, to some G in some biholomorphism. They have to converge uniformly on compact sets. So as long as you can get these guys to converge at a point, then, and they're all biholomorphisms of a hyperbolic guy, then you can actually arrange uniform convergence on compact sets with all derivatives. So this is actually going to converge to a biholomorphism, which is kind of a miracle. This is sadly the part where we pull the rabbit out of the hat and just say, well, see, that's why it's true. So this is a rather remarkable result, right? So you manage to somehow say that hyperbolicity is an extremely powerful property that controls something about automorphisms. Okay, so we've now therefore got that, so these Gn, after maybe taking a subsequence, go to some G, and the GnPn, the GnP or Pn go to P, and therefore GP is P. Okay, and now we'll have to worry about, does G preserve the foliation? But a foliation is determined by its tangent bundle, so the foliation is the same information as the tangent bundle of the foliation inside the tangent bundle of the manifold. And since the Gn's converge to G with derivatives, so they converge in, in C infinity on compact sets, they control they hold this thing invariant, right? That's exactly the property of preserving the foliation, is preserving the tangent bundle of the foliation. And so G must preserve the tangent bundle of the foliation, and that means preserving the foliation. So G is in fact a biholomorphism of M preserving the foliation, because that's really a local condition, or an infinitesimal condition. And so we have convergence forcing that. So we get an automorphism of the foliation, which fixes a point. So we get this rather remarkable object here. Okay, so what have we got? We've got the GNs approach G uniformly on compact sets, and so the PNs approach P, which means that the GNs, now the GNs take the leaf to itself, and the Gs take the leaf to itself, right? The GNs were, by definition, taking P with this leaf, taking it to one of the other Ps, which is on the same leaf. So it takes this leaf to the same leaf. So each of the GNs to preserve the leaf, because it took a point of that leaf to another point of the same leaf, and it was an automorphism of the foliation. So it preserves that leaf, and this preserves that leaf. And so what we get is Gn converges to G as an automorphism of the leaf. Well, in automorphisms of the leaf. But that means that GnP is Pn converges to P in the leaf. Okay, in the leaf. And that's not possible. Okay, so what we found is weird. It's somehow the fact that these P's approach this in this direction, but they don't approach in that direction. Okay, they're not allowed to approach across the leaf because it's too big. But they're allowed to approach as you go down this way through the ambient manifold M. And that doesn't work. It doesn't fit with these automorphisms, because we've managed to find automorphisms converging which would somehow make the PNs go to P down this way through M, but they have to preserve the leaf, so they actually have to act inside the leaf, and so they have to make the PNs actually move in the leaf in toward P. And that's not possible because this doesn't converge in P, in the leaf. Okay? So we've said that they all lay in different plaques, so they don't converge in the leaf. But here we've said they do converge in the leaf. Okay, so that tells us what? That tells us that, therefore, by that contradiction, that the leaves are closed. We suppose not, so we know the leaves are closed. Okay, so now we've got the leaves, and that's almost the whole story. That's pretty much the main effort. It took forever to figure out why the leaves are closed. And we've seen that there are examples of things that are not too far away from this kind of manifold where the leaves aren't closed. So closure of leaves is a very special, rare property, not expected. And so we get the main theorem that, let's say, N is a complex manifold, and pi, the leaf, so leaf space is a complex manifold, and the leaf map is a holomorphic. I wanted to prove it's a holomorphic submersion. So again, this was the leaf space, and this was the leaf map. And we want to prove this. And it's not, I'm not going to give a complete proof, but we can say that G modulo G leaf stabilizer is N, okay? And the leaf stabilizer is actually a closed subgroup of G because the leaf is closed. Every leaf is closed. So once the leaves are closed, their stabilizer is closed in the automorphisms of the foliation. And then this guy becomes a closed subgroup, and therefore this is a manifold. So N is a manifold. And pi is C infinity submersion. And then you have to prove it's actually holomorphic, which I won't get into. It's not particularly interesting. So okay, so that gives us, where are we now? Yeah. Yeah. What doesn't work for the torus? Okay. So if we look at the, suppose not, yeah, so the leaves are not closed. Let's see. So there are mad points. What doesn't work for this lemma here is that you can't get the automorphisms. Let's see, what do I want to say? It's a good question. Yeah, the question is, why doesn't this lemma work for the torus, for the case of the torus instead? So the torus is not hyperbolic, so wherever we really used hyperbolicity, somehow... Yeah, right, okay. So you might be able to get, yeah, so what is, yeah, what am we doing wrong here? It's a good question. Yeah, but he's saying, well, actually, you could get convergence there by using compactness of the translation group. So let's see. Why does it not work? Is 0 on the torus, right? Yeah. But ignoring the Kobayashi theorem and using compactness of the torus instead of the Kobayashi theorem, it looks like it works. Yeah. Obviously, it doesn't. It's a good question. I'll have to think about it. It's not clear to me offhand. Okay. So. All right. So we've got closed leaves. We've basically got the main theorem, and maybe I'll just point out a little bit about what I said about holomorphic submersions versus holomorphic fibrations. So again, maybe best to write the setup again. The M, throughout the whole talk, M was some hyperbolic complex manifold. That F was a holomorphic non-singular foliation on M. And that G was the automorphism group of, or biholomorphism group of M preserving the foliation. And we assume that G acted on M transitively. And we let pi take M to N be the leaf map. Okay, so that's the setup, again, just to remind us of where we were at the beginning. And what we were wondering about is what we could do better than this. It says it's a holomorphic submersion, and I said we could show it's not a holomorphic fiber bundle except in trivial cases. Let's just say, since I've got a few minutes left, was why that's the case. Sorry? I'm not quite catching it. Is the stabilizer connected? Yeah, it's a homogeneous space, yeah. Is the leaf stabilizer connected? I don't know, I can't think. I think it might be. I think we addressed that issue in the paper, but I can't remember. I think it's connected, but I don't remember. Okay, so yeah, sorry, it is, yeah. In fact, it is, yeah. The leaf stabilizer is connected. Yeah. But I don't know if we'll need to, well, okay, so let's just think about the following issue, which is that lemma that I think is somewhat interesting, that if pi takes M to N is a holomorphic fiber bundle mapping, then M is in fact just N cross the leaf G equivariantly. It's biholomorphic to that with a trivial foliation. So there aren't interesting examples where you get anything which is a fiber bundle mapping. Okay? So let's just see proof of that result. Is first of all the by a result of NAG, if you have a fiber bundle mapping with M to N, it's a holomorphic fiber bundle with M hyperbolic, then in fact, what do we get here? Then N is hyperbolic. Actually, I don't think that's really hard. You just lift maps of the disk, more or less. You just have more or less to sort of pull them up. So I don't think it's too difficult. And then there's a result, a rather strong result of Nakamura, which says that hyperbolic homogeneous complex manifolds are, in fact, what are they? Are convex domains. Okay, in CN. So they can be somehow embedded in CN. Okay, which is certainly not obvious. Right, so that's a fairly deep result that we have to use here, and that gives us that that implies that both M and N are convex domains. And so in particular, they're simply connected. Pi 1 of I want it to be pi 1 of N is the identity because it's a convex domain. And then there's a theorem of Royden what is the theorem? That pi 1 of N is 1 and pi takes M to N is a holomorphic fiber bundle map with M and N hyperbolic. That all that put together, which is exactly what we have, implies, in fact, that it's a trivial. Implies it's a trivial bundle. Okay, so it's a long song and dance through various known results. Okay, all right. I think I stop there.
Dense leaves. In the real case, for real foliations, when you have dense leaves, you can associate a convolution algebra in the sense of non-commutative geometry, even if all the leaves are dense. Have people done that in the holomorphic setting?
I'm not aware of that. I'm not aware. Yeah, it'd be interesting to think about. Yeah, I don't know. I don't know anything about it. Actually, I just think it's an interesting question to think about for the ball. It's just the two ball, for example. What does typical holomorphic foliations sort of look like, or how bad do they get? I mean, we sort of found one that has one non-closed leaf. We were sort of, struggling to think of, well, what? I mean, once one of them's not closed, it's probably all horrible. But we don't have no idea. We have no idea.